righty, we're back. Episode 7, Under the Scope podcast. Today I'm joined by Dr. Krishna Bhat, who is an organic chemistry professor here at Widener University. He also teaches biochemistry for nursing majors and food science to hospitality management majors. How you doing, Dr. Bhat?
I'm good. Thank you, Adrian, for having me.
Dr. Bhat, I think the first time I had you was the second half of Organic 1 during the summer. And Dr. Bhat it was a class of 6, so it always felt like he was picking on me and stuff, but I didn't really mind it actually. It was a fun class, I think. But
yeah, that's right. I remember. In fact, that's one of the misconceptions about me that people have, which I'll talk about it in more detail later.
Yeah. Dr. Bhat, I wanna hop right into this. So you're from India.
That's correct.
So I guess the first question is, where did your passion for chemistry begin? And how does the education of like chemistry differ from the Indian education to American education within chemistry?
Oh, that's an easy one. So I decided to pursue chemistry in my first year of college, actually. That's simply because I did not like biology. And I'll give you a specific example. My mom wanted me to go to medical school to become a medical doctor. So the first day we had biology lab. Lecture was not an issue, even though I wouldn't like it. I was a nerd, so I could memorize and, spill it out on the exam and to get a good grade. But when we went to the lab, the very first lab was to dissect a frog and nail that frog and identify the different parts and this thing. I took the thing in my hand, it started shaking and I knew I couldn't do it. So I had a lab partner who always wanted to cut things and this thing. He was into that. So I told him, why don't you go ahead and do all this cutting part and pin it down, then I'll identify the parts and then I'll write down the lab report and then, you can take it. So I came home that night and told my my mom, I'm pretty sure I will not be a medical doctor because I can't take these kind of things. If I can't dissect a frog, how am I going to deal with patients or, cutting? Yeah. So that was out of the question. So while I equally liked biology and chemistry, so right away that made up my mind that, I want to be a chemist. And there's something funny, as we progressed in the third year, as a chemistry major, we had physical chemistry and we had organic chemistry. And this is where I always think that how professors can make a difference in students' life. I loved physical chemistry because I liked the math component of it. I was very good at it. I was good in calculus, you name it, I had it. The instructor we had, he was very knowledgeable, but he just couldn't explain it to us at a level that we were able to follow. We had to study basically things by ourselves. And then here was an organic professor. He would start from one end of the board and he will write things on the board so clearly. He never erased the board once, making a mistake. That was it for me. I said, I need to be something like this guy one day. Mm-hmm. So my passion for organic chemistry was in the third year in the college. And,
right? This is your undergrad?
Yeah, this was an undergraduate, correct. And so after I graduated, when I talked to him about it, he said, if you are interested in becoming a teacher and you need to go further and do your PhD in organic chemistry, and that will give you more insight into what organic chemistry and how useful it is in terms of research and everything. So that's actually when I decided to go to do my PhD. Wow. So I got my PhD from this institute called Indian Institute of Technology. It's abbreviated as IIT. Now, talking about the difference in the education, it depends upon which college you go to in India. There are things like here that you have community colleges and you have places like Widener where you get more exposure to sophisticated instruments and things of that sort. So In IIT, your admission is provisional for a year because you have to, in that period of 1 year, you have to find a research advisor and do a little bit about research, not a whole lot, at least the background and stuff like that. But you have to pass about 8 out of 10 qualifying exams, what they call as.
Oh, wow.
So those qualifying exams basically test you everything you learned in your undergraduate degree, in organic, in inorganic, in physical, spectroscopy, everything.
Wow.
So they give you these qualifying exams every month so that you have to pass at least 8, and they are hard. I can tell you that they make it hard. Some of the things don't even have answers to it because they're all research problems that, you know, faculty have put in together.
What the?
So, I mean, I was lucky enough. Studying for exams and getting a passing has never been a problem for me because, I didn't have too much extracurricular activities other than just studying all the time. So I passed those exams, and then I found a research advisor who started with doing some research, and I wrote down the background, just like a proposal thing, right? And so the committee meets and say, okay, now you could be a research student at this institution. Then it takes about 3.5 years to actually do your, experimental work and write your thesis and publish papers, all those things. And so that's a difference. Like if you want to be, no, that's like an Ivy League school here, like a Penn and, Yale, that kind of stuff. Not everybody can get into it, even for a provisional period of time. They take only few and then make sure that, at least about 90% of whom they've selected are able to go forward.
Yeah.
So there are some, so we were like, we were using like IR and NMR back in those days. And I'm talking about 1980 at this point, right? So, but then there are other universities you can get your PhD from it, but then again, you won't be that well trained in terms of instrumental facilities because they just don't have it.
Yeah.
So getting an NMR, for example, under those times, because I know friends who went to those places and they had trouble getting the NMRs on a routine basis. So in terms of education systems, so there are some similarities. It depends upon which school you choose to go to. And then there are schools in which, people who are not very ambitious, but they still want to get a PhD and then get a local, job in a local, high school or a college there. And so that works for them, but it wasn't for me. I needed to be in a top school.
Yeah. That's awesome. I can relate to that, you not being able to do dissections, because I remember my sophomore year of high school, we were dissecting a frog, and I knew from the moment we did that, I was like, this is definitely not going to be for me. Dr. Bhat, I want to ask you another thing too. So you got your PhD from IIT.
Right.
So I guess this is kind of a two-part question. One is, did you want to go into industry, or have you always been in academia? And second, how'd you come into Widener? How'd you come to the United States and teaching over here?
Okay. So I always had a passion for teaching, so I always wanted to be a teacher. And then not just teaching, I wanted to get into a place where there is some opportunities for doing some independent research. But while I was writing my thesis and my advisor was taking his sweet time to correct my chapters and stuff like that, I didn't have much to do. So I took up a job in industry. It's called Unilever's, the company that makes the soaps and detergents and stuff like that.
What's it called again?
Unilever's, Unilevers.
Okay.
So that company makes, their money comes from making soaps and detergents and all those stuff. So they wanted to start a new research program to manufacture some drug intermediates. So that's where I got into, because, I always wanted to do something of a medicinal value. That's always been my target. So I took up the job, and then at the same time, I was applying to come abroad for postdoctoral work. So, and I wanted to work on amino acids, and that was one of my fascination. I never got to work about amino acids. I wanted to do that. So about 15 months or so later, I got a position open, and then I was invited to come. I first came to actually to Utah, to this country first. And that was quite a cultural shock, I have to say. I don't know. Utah, I don't know if you are aware of it. It's predominantly dominated by people called Mormons.
Yeah, the Mormons. Yeah.
Yeah. So they don't drink coffee or any caffeinated beverages. And I was a coffee drinker throughout the day. That was the first shock.
That's a cultural shift.
That's a sort of a cultural shift. Luckily for me, there was another person who came from Colorado at the same time I came to Utah, and he said, same evening he came in, I said, Krishna, do you want to go to Kmart and get a coffee brewer so we can have coffee? I said, yes, please. So I jumped on that opportunity, and then, so we had coffee going all the time. So that was it. So when I was there, I was very successful, and I had gone to a national American Chemical Society meeting in Chicago. And this is where this lady from University of Pennsylvania came up to me after that, and she said, do you have any plans to move to East Coast?
Ooh.
I said yes, but not to New York. I didn't want to go live my life in New York.
Yeah.
So she said, it's Philadelphia, so why don't you come and visit me and then see how you like our research group and what we do. And so, yeah, after a year and a half, and then I moved to Philadelphia, University of Penn, as a research associate. So after a year, I was mostly doing research, and then I started slowly teaching there. The first assignment was when she was gone on sabbatical. So I took her position to teach Organic 1 there.
Nice.
And while that was a great experience, because I had 189 students in the class.
Yeah, it's a big.
Yeah. I wore a microphone. We don't take any questions there in lecture. So, and then there were like 16 boards sliding up and down, so you never have to erase the board.
Yeah.
So you start from one end and you can use all the boards. But then my thing was, I didn't want it to be a teacher like that, not knowing whether the students understood things that I said, or it just went over their head. I wanted to be in like a medium type school, and that's when, so I started in Philadelphia University first. So, and then there were some.
Real quick. So is this all happening while you're still getting your PhD, or you already have it?
No, this is after PhD.
Okay, gotcha.
So while I was still getting my PhD degree, I was working for the industry. So I have some industrial experience, but then I quickly realized that industries, two things happen. One thing, they will tell you what to do. Yeah. Because what projects you have to work on, you don't have any control over what you want to do. So right away, that wasn't for me. And plus I used that as a stopgap arrangement because, instead of wasting my time while my research advisor is correcting my thesis or giving me feedback, I was getting paid. So that was a good thing to do. So in fact, people there also, like the research directors, actually support you in the sense that, if you have ideas of going abroad and all, you should start thinking about it. And, you need to build up your career, things like that. Yeah. So by then, by 15 months when I was there, everything was done. I defended my thesis. We're working on a project. They wanted to ask me if I can stay 6 more months. That's why it got delayed a little bit.
Gotcha. Okay.
But yeah, everything I'm talking to you after coming to this country is a postdoctoral work, which is after PhD.
Okay.
So after
University.
After Utah, then it was University of Pennsylvania.
Yeah.
And then so my actual independent teaching position was in Philadelphia University.
Gotcha.
It used to be called as Philadelphia College of Textiles and Science. When I was there, then it became a university. So, but then, things were good there and I was doing well. but the labs were very weak in terms of facilities.
Yeah.
And we wanted to sort of modernize the labs a little better. And the president would tell us to write proposals so that, we can get it funded. But when there was funding available, it went somewhere else. It went to building a parking lot one time. It went to building a university center. So after like 3 years, and I said, it's not working. So it's not going to happen because that doesn't seem to be their priority. So I started looking, and then, I did teach. First came here in Widener as an adjunct, actually. And then the same time I was teaching as an adjunct in Community College of Philadelphia as well. And the funny thing about it is the full-time position opened up in both places at the same time, in Community College as well as in Widener. So I had to make a choice because both places I got picked, but then Community College doesn't expect you to do any research or anything, for that. But my interest is not only just teaching, I also want to be doing some research. So that made the choice very easy and clear for me.
Nice.
And so I ended up in Widener.
Oh, wow. Yeah. I want to ask you this too. When was the first time you met Dr. Baston? What was that like?
It was, Dr. Baston was actually one of the pleasant experiences, favorite memories, I should say, is meeting all the people. While I came as an adjunct, and then I remember Baston was in the process of converting all the organic labs into green. That was the first time it was done. And then he said, we are going in this direction. And so I don't want you to change anything, he said. So I clearly remember that. I said, no problem. I won't change anything. I'll just follow your, manual and do the experiments. But then he also said that, as and when you think that something is working, something is not working, just keep a tab on it and let me know, and then we'll keep on working together. So, and he told me one time that, these are useful feedbacks because this is a work in progress. So it took a while for us to, to get to making all labs sort of greener. It took a while because some of the experiments we had to literally change and things like that. But overall, it was for me, everyone welcomed me with an open arm. Like, they were very nice. Anything you need, come and talk to us, and we'll be happy to help you. And Baston and I told him, it's not a secret, I've told him this before. He was a little skeptical because, here is a guy who has done these labs before in a different way. Then, if he becomes the instructor for teaching the lab, he was a little concerned that I might change the labs things to going back to a book lab or, things of that sort. But so that was one of the things he said to me that, please don't change anything. I said, no problem. And then it worked out well because I wanted to also, in fact, I was the first one to start a research project involving green chemistry concept. We started working on this Wittig reaction, which we still continue to do. You heard Victor talking about it recently. So
Victor on here, but he keeps saying no. He's like, he keeps pushing off. I'm like, Victor, get on here.
So,
but that was actually going to be my next question anyway. What is your current research projects that you do here at Widener?
So there are kind of 3 projects that I work on. One of them you might have seen is all has to do with greener synthesis, right? Making the synthesis greener, taking the current synthesis and making it greener, or try to find some other reagents which are, less toxic, and that kind of stuff. So one of them is derivatives of resveratrol, that's in the red wine, and now petrostilbene, which is sort of a cousin of resveratrol in terms of structure. So the idea came to me because, resveratrol, although it has a lot of medicinal effects, but it's very expensive. So I said, if we are able to develop a shorter sort of inexpensive synthesis, also in a greener way, that will be much cheaper, so it will be useful. So when I was talking about this to Dr. Cool, he mentioned that, what happens in resveratrol is the trans isomer is active, the cis isomer is not.
Mhm.
So that has always baffled us as to why these geometrical isomers are so different. So he said we could study some of the thermodynamic properties of these two compounds in different solvents like water and ethanol. So he said we can collaborate on those projects. And then it occurred to me, like, we want to make some derivatives which are also going to be more useful than resveratrol itself.
Mhm.
Now, we can make that in the lab, but it's not sufficient to make it in the lab. We want to test this out,
Mhm.
right? So when I was talking to Dr. Nagangas, she suggested that we could try it on fruit flies and see if it improves their movement, if it improves their actually the eye function, because and in fact, Sam Skoma, who just finished her biochem thesis and graduated, she worked on that. We found that when our synthetic compounds were injected in their food, they were very active, group was very active. And we fed this to the flies, which have Alzheimer's already,
Wow.
right? Yeah, they have, you can get flies which have Alzheimer's already, so which are sort of not looking very active and sort of this thing. So
Wait,
when
Dr.
they,
Bach, so is
yeah,
Alzheimer's a gene then? Like, is this a gene that you can pick out within the fruit flies? Like, how do you know that the fruit flies have like Alzheimer's?
so what causes Alzheimer's is this protein called amyloid that gets deposited in the brain.
Okay.
And so that causes not only just Alzheimer's, but all kinds of dementia, all forms of dementia. So the idea is if these compounds can help break up that plaque caused by the amyloid deposit, that will be very useful.
Mhm.
So that should also then make the flies more active because they will be able to, their brain function capacity will improve in terms of their functioning. So we did find that actually, we found that the flies were very active, and also some of the things that you observe in the eyes before and after, you could tell they're very active, right? They were very active in that. So, but this is a long way to go. So it all started with that. So, and the one part of, so it's like, a combination of making compounds in a greener way, trying to look at their physical thermochemical properties, and also testing them flies. So once that started, the other one I'm always interested is what are known as boronic acids. And boronic acids are these are compounds containing boron, and very little known about the synthesis of these materials,
Mhm.
because two of the compounds containing boronic acids are actually in clinical use. One of them for blood cancer, actually, when everything fails, they try this and it has worked.
Mhm.
But the starting materials to make these compounds, boronic acid derivatives, are very expensive.
Right.
So now what we've started looking at now, taking the boronic acid itself and see if we can make esters, or if we can make ethers or anhydrides that can be used as starting materials for larger pharmaceuticals.
Yep.
And we're doing that using the microwave. Now, now that we have a new microwave, we have jumped on that because we got success with the Wittig reaction.
Mhm.
Because the Wittig, we used to grind it for about 30 minutes, and we no longer
Yeah,
do
the
that.
warm
We put
vessel.
in like
Yeah.
6 minutes and it works. So boronic acids, this summer actually, Emma started working. Emma is a biology pre-PT major,
Mhm.
but she did some work on the boronic acid this summer.
Okay.
But the other one is, for me, based on the organic chemistry labs, is always look for greener synthesis. And one of them, of course, is the Williamson's ether synthesis. And we have done some progress. Instead of using the alkyl halides, we can use other stuff. And I also now want to try using something called dimethyl carbonate, which is a very environmentally friendly reagent to make methyl ethers. But I also want to continue that. If you modify the structure of compounds like vanillin, which is a flavoring agent,
Mhm.
and if you modify the structure to go to ether, it's a commercially used fragrance. So
Okay.
we're going into a new field of a family of fragrances actually using green chemistry.
Wow.
So yeah, that is still to take effect. Probably, hopefully, somebody in the FOAS, and when somebody comes and says, "I want to work with you," and yeah, that will be the project to start.
Wow. So yeah, I know. So you have 3 projects going on. I kind of want to, just for the viewers to know, I kind of want to break down your resveratrol synthesis and research real quick, because it might have been hard for people that don't understand chemistry to follow along.
Sure.
So basically, you start with, so resveratrol and their derivatives are in trial for Alzheimer's disease as a medicine for that, correct?
Well, resveratrol has already been done. It has been proven to be effective.
So,
right?
But to buy it, as it is, it's very expensive. So
Correct.
you found, you and your researchers found a way to synthesize it, right? For using base elements and base molecules and making it, correct?
We want to make, so it's also been suggested that if you introduce methyl groups into the resveratrol structure, they are much more effective. They increase the bioavailability and they require smaller amounts for treatment of Alzheimer's. So we want to make some of those derivatives.
Yeah.
Our focus is to make those derivatives from simple fragments, simple, inexpensive starting materials.
Gotcha. Okay.
Right.
Gotcha.
That's the thing. And put them together in a sort of concerted way, using a Wittig reaction, using the microwave, short period of time, saving energy, saving time, all those concepts. And, in majority of the cases, when we do the reaction, we just use water and the compound we're looking for separates out. So we are not using any solvents and things like that there.
Okay.
So yeah, our main goal is to prevent waste minimization, right? We work on producing a large amount of waste, and also use reagents that are sort of not toxic, because before, like, people used to use reagents like organometallics now, or butyl lithium, something like butyl lithium for a Wittig reaction. Your exposure of that is not good. Plus, you have to do reactions at very low temperatures and things like that in the presence of inert atmosphere. So all these goes away when we do this using the microwave for a short period of time.
Right. Yeah. So I think green chemistry is always should be a priority, right? So I mean, I think that's like, using non-toxic solvents, less energy, all that stuff. I mean, that's always a priority.
Yeah, it is. And a lot of industries now are also, interested in switching to totally green chemistry processes. That's why the huge investment there. And so when people graduate and go to workforce, they are ready for it because they know what it's all about. That's another advantage.
So you have this green synthesis of resveratrol derivatives, and then you paired with Dr. Nagengas to actually test those on fruit flies.
Correct.
So was there any success there? You found that they're more active, right? And they have more eye movement?
That's correct. So
now,
we have
so from a biochemistry perspective, and like I guess, how is that credible, right? So like if I'm just coming along here and I don't know anything about research, how do I know that just because they're more active and they have more eye movement, that correlates to the resveratrol derivatives that are working on the fruit flies?
So we look for certain improvement in the symptoms, what was there before in flies, in regular flies versus the flies which have Alzheimer's, right? Their movement, their behavior, their lifespan, how long they live, and also the function of the eye is very critical as well. So when you see this as from before and after sort of thing, when you injected your synthetic derivatives in their food, because they have to consume the food, so they're consuming your compounds, then you see the behavior changing. So these are preliminary studies. But then these are promising preliminary studies, I want to say. because they are certainly encouraging. A lot has to be done before, this can become a, I don't know, it may take about 8 years or so to have everything that, yes, this particular derivative that you have chosen is going to be working really well for Alzheimer's and related dementia disorders. So it's a long process.
Yeah.
But at least the thing is, we need to make, at Widener, at least we have the flies that we can test. We don't have rats, or we don't have other animals and things like that. So within the limited capacity, but we've been talking to people in the medical school in Temple, and they are very interested in it. So that's going to happen at some point in time. So they have more testing capabilities on other animals and stuff like that.
So the fruit flies can give you a good estimate, right? So they can probably give you a pretty good estimate.
Yeah, because see, the 86% of the fruit flies, they match with the human gene. So it's a good gene matching there. So when it works on them, then it gives us an idea that, yes, you can take it to the next level.
Dr. Bhat, is there a paper or a presentation that I can include in the YouTube video so that if people are more interested in kind of getting a little bit more insight that I can attach to this video, or is there not one?
So we are actually currently in the process of writing these things, so it's not available yet.
Okay.
But a lot of students have done presentations
on the synthesis, right?
Yeah, Sam Skoma, people like that have given multiple presentations on this, not only here, but also elsewhere as well.
Okay.
So those presentations are there that, that people have access to.
Okay. So what I can do is, when you start wrapping this up, and then once you start coming to conclusions, maybe we can hop on again on another podcast in the future, and we can talk about the results. That'd be pretty interesting.
Sure. That will be nice.
Yeah. But okay, so I want to shift gears a little bit. So we talked about your research, we talked about your background. What do you think some of the misconceptions are about you, and the misconceptions about, chemistry in general?
So misconceptions about me, like you said earlier, people think that I pick on them.
Yeah.
So although nowadays I started telling that it's not that I'm picking on you, I just want to know if you are on the same page as I am, or, and I tell them you don't have to know the answers to the questions I'm asking you. I'm not expecting you to say, but I'm sort of want you to think about what is it that I'm looking for, so yeah, I do call upon people, but nowadays I also, but once they get to know me, because, in my office hours, once they know that I'm very approachable easily and I'm very friendly, that goes away. But in the beginning, the very first class or second class, when you don't know me, in a large class of 70 people, if I'm picking on one or two, then they're like, oh my God, he's picking on me.
Yeah.
So that's a regular misconception that I've heard before. In terms of chemistry, I'll say mostly because I've taught organic for a long time now. So people have this notion that it's a very hard and difficult subject, right? Which is not the case. It has a very notorious reputation of being difficult and hard. And part of the reason because, people, pre-med students would say, well, if you succeed in organic, then, you'll be in good shape and stuff like that. So it's not really true. It will require some decent studying habits. It's not something that you can put off till the 2 days before the exam and then you think you can catch up.
Yeah.
But right from the beginning, if you set some time away to study on a regular basis, and in my case, if you're coming to the classes and following what I'm talking about, if you're able to do the problems that I ask you to do again in my worksheet problems, if you do the problems that I'm asking you to look at in the textbook nowadays, every chapter I point out, these are the problems that are going to be really useful. Because I want them, there are certain concepts I want them to get really well moving forward to Orgo 2.
Yeah.
You know, even if they've forgotten a few things about, okay, which is the most stable conformation, least stable conformation, okay, we're okay with that.
Mm.
But something like, you know, mechanisms like SN1, SN2, E1, E2, you know, you need to be solid about this, because we spend a lot of time talking about those reactions, stereochemistry, mechanisms. We create, we start talking about how it is utilized in synthesis to make other compounds, but it goes much more in Orgo 2. So if you have a solid background of this, the Orgo 2 will become much more easier. And even Dr. Bastin and we always talk about this, and that is, we think that Orgo 1 is much more harder than Orgo 2 because you have a lot of different things coming to you. Yeah. Because once you start with the dot structures, you have this resonance concept, which I've never seen. You talk about stereochemistry, you know, the R isomer, S isomer, diastereomers, what are they? We talk about
Fisher diagrams. I remember those.
Yeah, conformations, and then we get into the mechanisms, the elementary steps, and all this stuff. So there is variety of things coming in there in Orgo 1. But if you get a good solid foundation about these things, you know, your Orgo 2 will flow very smoothly because you're basically applying that to different reactions. So you're going to apply it to more of synthesis, more of the mechanisms, and things of that sort. Yeah. So the misconception I say is usually that, you know, people think that it's hard and it's difficult. That's the misconception. So
yeah, I think I can definitely attest to that, because I think a lot of people get so caught up in I mean, like you said, like it's a lot of things throwing you at once. People get so caught up in the conformations and you know, I gotta memorize. I don't even know. It doesn't even matter. But the point is, are you understanding? You know, what is an electrophile? You know, what is a nucleophile? How does this molecule look in 3D? Would it actually make sense for it to be attacked by a, you know, and a nucleophile there? Like, would it make sense if it's bulky? You know, whatever. Those are the more like concepts I think people got to understand. And if you try and memorize the mechanisms that you get in Orgo 1, you're not gonna be successful, because you're gonna drive yourself insane. You need to understand the concepts.
So that's why I keep telling people, okay, you're looking at an electrophile and a nucleophile. Electrophile is electron deficient. What is an electron deficient thing? Something that already has a defined positive charge is an electron deficient species. Or if you take an alkyl halide, where you have a carbon halogen polar bond, carbon, because of the polarity, carries a slight positive charge, it is an electron deficient species. If you take a ketone, there's a strong dipole between carbon and oxygen. The electron pull is towards oxygen. Carbon is slightly positive. That's an electrophile. Nucleophile, same way. Water with a pair of electrons, anything with a negative charge is an electron-rich source. Or, you know, there's no difference between alcohol and water. Think of alcohol as one hydrogen is replaced by an ethyl group, but still does the same thing. You still have that oxygen with a pair of electrons. So if you start seeing this in a general way, right? A general pattern, things will become much more smoother. Yeah. So that requires understanding of the concepts clearly and trying to apply it. So.
And I think you and Dr. Bass have done a great job with changing kind of the organic lecturing in that way. It's more conceptual, and look, there is some memorization at the end of the day, but it's mostly conceptual, and you guys really do try to, like, you know, help your students out. So yeah, I think I was gonna ask one more thing. What do you think is the biggest, what was, from when you first started here at Widener to now, what do you think what was the biggest change that you and or Dr. Bastin implemented as far as a green chemistry initiative, both in the labs or maybe as a lecture? Like, what do you think was what was the biggest change?
Well, first we started with the labs. Labs where, you know, once we got things under the labs, then we started doing in the lecture to bring about, whenever we talk about new reagents, then we talk about why this is a greener reagent now as opposed to what we used to do before. If you want to convert an alcohol to a bromide, you could use HBr, but HBr is not a very green reagent. Now we have a reagent which is PCl3, which is phosphorus bromide, and which is much more easier to use, and it's greener. So we started like talking about it, like even for example in the Wittig reaction Bastian talks about, and when I substitute for him and I would talk about the same thing, is that we used to use reagents like strong bases like butyllithium, which are toxic and this and that. Now we are doing this using things like sodium hydroxide. And we have now even come to the level of using something like potassium carbonate, sodium carbonate. Carbonates are the weakest bases you can find. And, you know, a carbonate falls in your hand, nothing will happen. It's very, you know, and cutting down the temperature wise, you can do these reactions at room temperature or slightly higher using microwave. So when we now talk about those new reactions, then we do a comparison, like the traditional way it used to be done. Now, what is the greener way it is done? So we started implementing that in our lectures. Not much happens in Orgo 1 in terms of those kind of comparisons, because it's only chapter 10 that we get to where I talk a little bit about green chemistry and synthesis and those reagents.
Okay.
But he does a lot in Orgo 2. And when he was on sabbatical, I taught Orgo 2 and I did the same thing. We do very similar things. We don't differ a whole lot in terms of our teaching. Our teaching styles might vary a little bit, you know, because it's individual. But then delivery of the content, it's the same.
Yeah, no, for sure. What do you think is what do you think is like one of your favorite Widener memories, and then maybe like your proudest moment as like as a research advisor?
So of course, the proudest moment at Widener is getting some awards. I have won twice now, which is called Clarence Moll Professor of the Year Award.
Well deserved, yeah.
This award is actually given by Student Government Association. SGA gives this award. What they do is they send out a survey about, you know, who is your favorite professor and why is that, and you need to justify. And I won that twice. Yeah, I really like that and cherish that because it's coming from students. So I tell the students that I have done this a lot of times now, so please take advantage of me. Whatever you need to know, I'm here, knock on my doors. I have office hours, but I also have a policy of open door policy. And I had to explain sometime what that means. I tell open door policy means if my door is open, you're welcome to come and ask questions, right? Yeah. So my whole effort is to strengthening and helping them in any way I can. In research, I have seen students first coming in, little timid, and slowly then they start opening up. I've seen them growing, right? Not only in terms of research, they are able to think independently and suggesting like, okay, why don't we try this? And in fact, you know, this concept of trying carbonates came from a student. Actually, she said, can we actually make it a little more greener by using carbonates instead of this? I said, go ahead and try it. Because, you know, research is not something that's set in stone. Unless until you try different things you don't know. So to me, having seen them growing, not only professionally expanding their knowledge in research, but also as a person, then you get to know the person really well. You do that, and when they graduate and go out, they're still, you know, Connolly Richards was one of the best students I had. They're still in touch, and they tell me what kind of projects you're doing. And the other day, he sent me an email about polymers, and I think I want to try this, and what do you think about it? And I just looked at it and found a couple of papers which have done similar work, and I forwarded that to him. So yeah, having seen them as students first in Oregon 1 class, and then having seen them mature to the extent how they become independent thinkers and able to do projects, and now going outside and doing great work, that is very
rewarding. Gratifying.
It's just so rewarding. It's unbelievable. That's the joy that I get when I see things like that.
That's awesome. Dr.
And of course, when the students recognize you and then you get an award from the university, awesome.
Yeah, no, I think your awards are definitely well deserved. I don't think anyone I just certainly don't dispute it. You do great work here. As we begin to wrap up here, Dr. Bott, what is like some advice that you give to prospective chemistry students, maybe like just students in general? Like what do you say to students?
So what I would tell them is you need to dream big. Don't hold back, because anything is possible if you put your mind and energy into it, right? When you come to a college as a first year student, you may not know what avenue to pursue or what area you want to be. You don't know that. That's okay. No, like Demi Lovato says, it's okay to be not okay. She has a
Demi
song on
Lovato
it.
said that.
Demi Lovato has a song. It's okay not to be okay.
Oh, he
Yeah,
keeps.
I listen to some songs as well.
That's awesome.
I have 1 hour drive, so I listen to music sometimes.
Heck yeah.
So the thing is, when you are here, you are exposed to the opportunities in here, right? You can find your interest in what is it that interests you and go along that pathway. This happened to a daughter. I tell you this. She, after high school, she went to Penn State, and then she was under this misconception that I wanted her to be a science major. So after during the first semester, when she came back for Thanksgiving, she said, I don't think I want to be a science major because I don't like chemistry and biology and all this stuff. I said, we never told you to be a science major. Where is this coming from? So I told her, go back in the spring and take a class in a business school, take a class in computer science, take a class in psychology, and see which interests you and so on. So they decide, she liked the business aspect of it. Graduated, as a business management major. And then while she was, they have the campus recruit, she got recruited by Capital One.
Wow.
She worked for them for 3 years and then started her own consultant business, and she's very successful, right?
That's
so
awesome.
You don't know when you're coming, but then you need to dream, have something that what is it that you want to become in life. So, and don't put any restrictions on it. Don't put any financial restrictions, so that we can find a way to overcome this. We have scholarships, we can find other ways how things can be supported. And then you get exposed to a lot of different pathways here. And then that's when you need to start building it up. What is it that I do? It's not that you need to take your parents' advice that, oh, I want you to be a doctor, I want you to be a thing like that. Because, and I've heard this, I'm sir on the health advisory committee, and then some of the students who come as pre-med have changed their mind because, they realize that's not what they want to do.
Yeah.
So, you choose one thing I will tell you is whatever you find your interest in, excel in that.
Yeah.
Go to the highest level. My dad always used to say, either you do things properly or you don't do it. It's as simple as that. And I got an advice from my after I graduated in college that he said, go all the way, get your PhD and be the best professor you can be, and you also will able to do research. And I'm thankful to him for in fact, the first time I got a student evaluation, I took it to him to show it to him, well, to rub his nose. So but yeah, that's what it is. You need to come with an open mind and then look for the opportunities that you think that you like and go for it. Dream big, go for your dreams.
Yeah, I agree. I agree 100%. I think a lot of people are closed-minded, and they come in with one thing, and they want to stick to it. But I think that you owe it to yourself to find what you love to do. And once you do, like once you find your niche, you have a duty to the entire world, to yourself, to be the best that you can at that goal or whatever it is.
That's correct.
And it doesn't matter what it is. So
no, it doesn't.
So. But you owe it to yourself. Well, Dr. Bott, it was so good. First of all, it's so good seeing you. So good talking to you. It was good seeing you the other day passing by. I want to thank you for hopping on the podcast. I know I greatly appreciate it, and I appreciate your time. And hopefully we can do this again soon, Dr. Bhat.
Sure. I really liked it. I love talking to you. Again, thank for the invitation, and we'll do it again, as you said, sometime.
Yeah, for sure. All right, everyone. So this will conclude episode 7. If you enjoy this stuff, make sure you like and subscribe, and we'll see you next time.
Then you're left in the dust, unless I stuck by you. You're a sunflower. I think your love will be too much, or you'll be left in the